So I think we can go ahead and get started in just a minute. Haley, do you mind linking the doc again for anybody who has just joined? Perfect. Haley has just placed that sign-in sheet in the chat again. If you don't mind filling it out, that would be wonderful. So for anybody just joining, and I'm sorry for the folks who've heard me say this 5 times already, I'm Anna. I'm the Senior Data Scientist at Catalist, and I'm going to be telling you all about data and models today. So I'm going to go ahead and share my screen. I'm going to go ahead and get started. For anybody who is still trickling in, they'll just have to catch up. So I'm going to share my screen and going to full screen my presentation. All right, so hopefully you all can see this. So today we're here to talk about best practices for using data and models. As I've said many times already, my name is Anna. I'm the Senior Data Scientist at Catalist. And I am just so excited to be here with you all today. I know that for those of us on the East Coast, this is our lunchtime. I know that it's virtual. I know we can't be together in person. But I'm just so glad that you're here, and I hope that we can make this a really fun and interactive experience. As you come up with questions, please put them in the Q&A box, and I will answer them at the end of the presentation. If you have any technical difficulties, please let our tech volunteer, Joan, know in the chat, and she will help you. So let's get started. So first of all, a little bit about Catalyst. So some of you may actually know Catalyst. Some of you may not know Catalyst by name, but may be familiar with our data. So we provide a national database as well as data and analytics and modeling services for the progressive movement. So if you've ever used the LAN, if you've ever used the America Votes or State Voices van, you've actually interacted with our data already, and you might not even have known it. So we provide this updated, continuously updated national database of around 240 million unique voting age person records. It's a lot of data. It is nationally persistent and unique IDs on data, person, household, and address identifiers. And then we have this analytics database, which includes actually over a decade of historical data for longitudinal analyses. And so this is the data that I use when I'm building the models that we're talking about today. So that's who Catalyst is. What is a predictive model? This is probably the question that some of you might know an answer to and some of you might not. Before I really get into the meat of it, let's talk a little bit about statistical models. There are so many kinds of statistical models. They range from time series models, which you might have seen used to forecast economic growth. They range from cluster models, which maybe you have seen used to group survey respondents into segments based on their responses. And they also include individual level predictive models. For example, predicting something about each person on a voter file. So this is not an exhaustive list of the different kinds of predictive models that are available. However, it's an example of the sorts that are out there. But for today, and for the rest of this presentation, when I use the word model, I'm talking about this last kind. I'm talking about this individual level predictive model. Just know that when you use the word model in your day-to-day life, it might mean something different to the person you're talking to. So I'm trying to be very clear about what kind of model we're talking about today. All right, so what is an individual level predictive model, Anna? You are hopefully wondering. Well, I'm going to tell you how to use it. So we use a predictive model only when we don't or can't know something for sure. So for example, if we want to predict somebody's opinion, does a person support abortion rights? Well, we can't ask 240 million people if they support abortion rights. We can't know it for sure. but we can predict it. We might want to predict somebody's future behavior. Unfortunately, I am a data scientist and not a magician, and so I can't actually predict the future, but I can try. And so if we don't know what's going to happen in 2020, for example, will a person vote in the 2020 election? We can build a model that will predict that. And another reason that we might want to use a model is if we need to predict someone's current state. For example, is a person on our voter file married? Now, you might think that this is actually something that we could know about all 240 million people. But the answer is that we can't, because this data is not publicly available anywhere. So in order to try to know if somebody's married, we can't know for sure, but we can build a model to predict it. So here's an example of a model. And this is actually, all of these models are models that Catalist provides. These are real scores that I'm talking about today. But let's take for an example, the abortion support score. So this is a model that predicts whether someone is likely to support access to abortion. And this is provided for every person on the voter file as a score from 0, which means least likely out of everybody, to 100, which means most likely. So when you as practitioners are interacting with models, what you see them as is a number, primarily. You're going to see them as a number associated with a person. The abortion support score is a ranked likelihood score. It is italicized because I'm going to talk about that a little bit later. Another example of a model is something that we have that we call the vote choice index. And this predicts whether someone is likely to support the Democrat in a typical two-way competitive election, so Democrat versus Republican. This is similar to partisanship, but it's less about how you identify and it's more about how you actually vote, which in many cases is a little bit more useful. So this is provided as a probabilistic score, again italicized. Again, I will talk about that later. From 0, which means not likely to support the Democrat, to 100, which means very likely to support the Democrat. Again, if you interact with this score, you will see it assigned to a person as a number. So a third example, we talked about marriage a little bit earlier. We actually have a score that predicts if somebody is married or not. And so this one's a little bit different because if you see it on our file, it's not going to look like a number. It's going to be a category, married or not married. And so this is what we call a categorical score. And the important thing to note is that this is still a score, even though it doesn't look like a number. So those are some examples of real-world models that we provide for folks to use. Let me talk a little bit more about the different types of scores, because I mentioned 3 types. So the first type that I'm going to talk about is a probabilistic score. This is a score that has the most meaning encoded in it. So a probabilistic score, they generally range from 0 to 100. And what that number means is the actual real world probability of something being the case. So with the example of vote choice index, the probabilistic score means that if I have a score of 80, on a scale of 0 to 100, I have a score of 80. That has real meaning, that 80. If I had 100 people who all had scores of 80 like me, you would expect 80 of us to actually vote for the Democrat and 20 of us to vote for the Republican, because it's that real probability. That's like 80%. That's what that score means. It also effectively rank orders people from least likely to most likely. So you're able to use a probabilistic score to select people who are most likely to, say, for example, support a Democratic candidate. The second type of score that I'm going to talk about is a ranked likelihood. The abortion support score that I mentioned earlier is an example of this. So what a ranked likelihood score looks like It looks a lot like a probabilistic score. It's also 0 to 100. It's also a number. But what this does is it doesn't have actual meaning encoded in the number. It's not representing a real world probability. It is just rank ordering people. So if I have a score of 80 on the abortion support score, all that tells you is that I am more likely to support abortion than 80% of the rest of the people in the country if it's like a ranked percentile. If somebody else has a score of 60, then it means that I am more likely to support abortion than the person with a score of 60. If there's a person with a score of 55, they are even less likely to support abortion than the person with a score of 60. It's just a rank order. And again, it looks like a probabilistic score, but it's not. It doesn't have that same inherent meaning. And then the third type of score is that categorical score that we talked about with marriage. So categorical scores look like a category. In many ways, it looks like something that maybe we know for sure. It says this person is married. But because it's a score, there's actually a number underlying that category. There's a numerical reason that we decided that the person was married or not married. But what we provide to the folks who we work with is the category, because you don't need to know that I have a marriage score of 60. What you need to know is, am I likely to be married or not? And then you can create, your universes accordingly. So you can see scores presented in different ways, but underlying all of them is a number, even if you don't see it. So I talked about scores. Let's talk about models. Models use known data to predict something unknown. This is a key concept that I'm going to go back to again and again throughout this presentation. So let's just look at this a little bit. Models use known data to predict something unknown. This is my sort of rough approximation of what a model kind of is. It looks like math. It's not math. I made it up. I will explain it, so bear with me. So I always think of a model as having two steps. The first step is where you have some data. And you have an outcome, and then you have data. And I'm going to talk a little bit more about those two different parts. But think of that as just having some data. You take an algorithm, and you sort of wrap that data in an algorithm. And it generates rules. Rules about how to get that outcome out of that data. Then you take those rules, and you give it different data. And those rules applied to the new data generate a prediction. The rules are the model. The prediction is the score. So we use colloquially the term model and score interchangeably in many cases. But when you're working with model, if you come to me and you say, Anna, I want you to build me a model, I will build you a model, but what I'm going to give you is a score. So this is a bit of a terminological thing, but I think that it's important that we remember that a model is the rules, and the score, that prediction, is the output of the model, and that's what you're actually day-to-day working with, is that score. So I apologize if I mess up and call something a model when it's actually a score in this presentation, because we all do it, but that's the difference. So I promised you I would tell you how to build a model, and that's what's up next. So the first step in building a model actually has nothing to do with data, and it has nothing to do with math, and it has nothing to do with computers. The first step in building a model is figuring out what you're actually trying to do with it. I need you to define the question. If somebody comes to me and says, Anna, I need a model, I don't say yes for what. I say, what problem are you facing? What are you actually trying to do? Because sometimes this is the step where you're going to figure out if you actually need a model at all. Let's go through some examples of what a good question might be in order to build a model. So maybe you want to know who is likely to agree to volunteer for my organization. Maybe you want to know who is likely to vote for my candidate. Maybe you want to know who is likely to support the cause of my organization. Maybe your organization works for gun control or an environmental cause or racial justice, and you want to identify supporters of that cause. Maybe you want to know who is likely to view my Facebook advertisement. The one thing that I want us all to notice about these questions is that they begin with the phrase, who is likely? This is an individual level predictive model. Likely, predictive, individual level, who? These are questions that you can answer with that kind of model, and you can then use them to create lists of people who are good contacts, who you could call and ask them if they want to volunteer for your organization. And because they're likely to do so, you'll get a good response rate. You could create a list of people who you want to do get out the vote work with in order to help them vote for your candidate because they are likely to be supporters. If you want to do Facebook advertising, you might want a list of people who are likely to see it so that you're not wasting money. These are all the kinds of questions that you can ask that an individual level predictive model can help to solve. If you can't in any way reframe your question to sound something like this, then my guess is that you don't need a model. But this is the step that you should work with your data scientist, with your analytics team, with your vendor. When you ask for a model, this should be the first thing that they help you do. And if they don't, then you need to take that initiative. Because if you don't define the question correctly, then your model is going to be useless. A model is a very specific tool that serves a very specific use case. And so defining that use case is the most important step. So I've lectured you enough. Hopefully you all know now that when you think you want a model, you should sit down, really think about what it is that you need. But let's decide that we need a model, and we know we need a model, and we've defined our question. So now we're into the data part. We need to collect the data. Unless you are very, very lucky, you will need to do some work here. You will not necessarily immediately have everything that you need. So that's primarily the case with what we call the outcome. And you might remember this from the previous slide. So what is an outcome? This is really the answer to your question on a small subset of people. So for example, let's say you wanted to know who is likely to support my candidate. Well, you could do a survey and ask people, do you support my candidate? And now you actually have the answer to your question. And so that is what we talk about when we talk about an outcome. Remember, models predict something unknown from known data, right? So we need to give it examples of what it's looking for before it can know what to look for. So the second part of modeling that you need for the data are the inputs. And this is data that you know about everyone who you are trying to predict. This is going to be the known data that the model uses to predict the unknown, to predict the outcome. So examples of inputs, primarily voter file data. That's the basis of all the work that we do and all the work that most folks in the progressive space do. We also purchase commercial data that has information about people's consumer habits and other things about them that we append to the voter file. We can also use what we call synthetic data, which sounds fancy. It's really things like other model scores or aggregates. And we also like to use census data because at least up until 2020, the census has been really great and a really reliable data source. And so the good thing for all of you on this call is that you don't really have to worry about the inputs because that's what we do. That's what Catalist does. Catalist provides all of those inputs. You know, your vendor or your database That's your inputs. You should already have this information. It's the outcome that primarily you're really going to have to go out and collect. Okay, so we have inputs that we can try to use to predict our outcome. How do we actually do that? So this is a step called training the model, which I like because it makes it sound like a puppy or something. You know, you have to train it. So the first step in training the model is that you split the data into test and train sets. So you have all your data right here. You went out and you collected your outcome, you have your inputs, you've joined it all together. It now exists in this lovely big data set. You probably want to scramble a little bit randomly and save some to be your training set and some to be your test set. And I will go into what the differences are. But let's just keep in mind right now, we have now split up our big data set into 2 other data sets. Then we train the model on the train set. Makes sense? And so this is where that first part of what a model is comes into play. We have our outcome, our survey responses. We have our data, all that good voter file, census, commercial stuff. And we apply an algorithm to it. And what the algorithm is going to try to do is find connections between the outcome and the inputs. And it's going to do that not using magic. It's going to use math. And the algorithm is going to work all its math, and it's going to come up with rules for how to turn the data inputs into an outcome. That's all that is. So we've trained the model. How do we know that it works? So we have to validate it. So fortunately, we already split it up into a test set and a train set. The fun thing about that test set is that our model, that algorithm, has never seen the data in the test set. It only ever saw the data in the training set. So this is like this totally separate set that we can use to make sure that the model actually found some good patterns, that the patterns that it's using to turn input data into an outcome, into a prediction outcome, is actually working. But the first thing that we need to do is actually generate some predictions for the test set. Those predictions, scores. So this is that second step of the sort of fake equation thing I showed you earlier. This is where we take our test data, and remember, we're not using the outcome now. We're just taking the input data. We're applying the rules that we generated from our model. We're applying our model now to this data, and it's going to give us a prediction. And so now what we can do, because the test set does have an outcome associated with it, we do know the answer. We're predicting the answer, but we actually also know the real answer for this test set. We just line up the predicted scores with the actual outcome. How close did we get? Is there a good relationship there? Does the prediction generally align with the real outcome? If it doesn't, you really got to start again. You know, I'm not going to go into how you know if your model's good enough, because whether the prediction lines up pretty well, okay, extremely well with the outcome is really going to depend on the data you have available. It's going to depend on the question that you talked about in the first step. It's going to depend what your use case is, what is good enough. But I'll give you an example of a really good model that's very good at predicting the outcome, which is going to be the vote choice index score that we provide. So this is where y'all got to hang on to your hats. We're going to dive into some visualizations. I will explain all of it. So just bear with me. Nobody panic. So let's look at the x-axis, which is this horizontal line down here. This down here is the vote choice index score. This is the prediction. It goes from 1 to 100, and it's in bins of 10. So lower to higher on the right. Over here on this y-axis, on this vertical line, this is what actually happened. This is real life. This is the Democrat candidate support percent. And it goes from 0 to 100%. So what you're looking for with a validation plot like this is you want to see people who we gave scores in our test set from 1 to 10. And remember, this is probabilistic, so we think that means like 1 to 10% likely. In reality, what is their actual Democratic candidate support? And we see that it's about 10. It's about 10%. If we move to our next bucket of our scores from 11 to 20, this is slightly higher probability of supporting the Democratic candidate. In reality, what happened? Did they have a higher probability of supporting the Democratic candidate? Did they actually support at a higher rate? And they did. You know, it looks about 20%. We move up the bins, and as we move up the score bins, as the score increases, as that probability increases, we see that the real life vote share also increases. And so what you get is this lovely little stair step kind of chart. And you see that, you know, as every score increases, they increase by the same amount of real world vote share. And that means that the model is well calibrated. It's a real probability. It's reflecting the actual probability of supporting a Democratic candidate. And so this is my favorite kind of chart to show people. If you've ever been on a webinar with me, I do a lot of webinars for Catalist on models. You know that I love this kind of validation plot because I think it really makes sense. It really helps you understand not only how well the model works, but also what to expect when you use the model. So for example, let's say, you know, I don't know how many of you are all hard side or if some of you do C3 work, so just bear with me, we're in a hypothetical universe. You want to get out the vote work for a Democratic candidate, and you have this vote choice index score. If you talk to people who had scores of 90 and above, based on this validation, this is at about 90% right here. Based on this validation, you would expect that if you talk to a universe of people 90 and above, 90% of the people you talk to would support the candidate. You'd only have to talk to 10% Republicans. Still more Republicans than I ever want to talk to, but you know, it's not bad. It's especially not bad for your volunteers. You know, if you lowered that and you went to 70 and above, you'd be reaching actually about 75% of the people that you talk to would be Democrats. So you'd only have to talk to 25% Republicans. Again, that's not bad. That means that you have successfully eliminated, you know, the vast proportion of folks who are not going to support you, and you've really been targeting only the people who are more likely to be your supporters. So this is the value of models, and the value of this validation charts is that you can look and see if I actually take this model out into the field, I take my scores out and talk to people, what is the real world percentage of people who support me that I'm going to be talking to? And so that's the beauty of these charts. So that's the validation. Right now, we've all been talking about our little test and train sets, our little small subset of data. But we don't care just about a small subset of data. We want to know everyone. We want to know all 240 million people. What do they think? So we have to score the model. This is sort of a phrase. It just means create scores for everybody using the model. And so again, we're going to take now not just our small subset of data. We're going to take all of our data. We're going to take everything in that database, and we're going to apply the rules to it. We're going to apply the model to it, and it's going to give us predictions for every single person on our file. what does this actually look like? So this is a histogram, and it shows the actual scores of people on that vote choice index score that we provide in red. So again, down here on the x-axis, starting at 0 and going to 100 is our score, is our prediction. And over here on our vertical axis, on our y-axis, we have the number of registered voters who have that score. So this just shows you like how many people have low scores, how many people have high scores, how many people have medium scores. And so what we see is that we have, this is bimodal, we have 2 peaks, one in the very low end and one in the very high end. So the model is able to identify a lot of folks as very likely Democratic supporters over here, or very likely Republican supporters over here. But then we also have a pretty solid chunk of folk in the middle who either maybe we don't know much about, so we don't want to say anything either way, or they're genuinely, you know, in the middle, you know, ticket splitters or ideologically moderate that are in this sort of score range in the middle. And so we can learn a lot from actually looking at the score distribution of everybody on the file. Okay, so I showed you a lot of charts. Hopefully, you know, some of you are practitioners, and what you want to know is, how do I actually use the model? Scores, because you're using scores. I use the model to give you the scores. So primarily, you want to use them to create lists for voter outreach using score cutoffs. And what I mean by a score cutoff is something like 70 or higher, or 50 or higher, or 90 or higher. Just using a cut point on that score and saying, I'm going to talk to people who only have scores that are higher than this. And these lists are things like, you can make phone calls from those lists. You can do peer-to-peer texting. In a previous world, you could do canvassing. Hopefully we're all staying safe and wearing masks inside. Or you could use them to make digital advertising lists. And the thing to remember is that you want to make sure that these lists you're creating are representative of who you want to reach. We're about to get into why I'm telling you this, but I want to put it in more than one place in this presentation, because if you take anything away from this presentation, this is what I want you to take away. If you're creating lists using scores in Van or something, always check those lists, run some crosstabs, run some counts, you know, by demographics, and look, does this list look like the people I'm trying to talk to? If you create a list and you've used a bunch of different model cutoffs and you've used some geography, and then you look at that list and you see, oh, it's all older people, it's all people over 60. Is that actually who you want to target? And if you find that this is happening, you go back to your data scientist, you go back to your vendor, back to your analytics team, and you ask them, how can I use this model in a more effective way to get a more representative universe of people to talk to? Because we believe that all people are important to talk to, and that we shouldn't just, even if the model says so, talk to one specific demographic. The model says so is never an excuse. So let's go into what I mean by that. We talked a lot about what is a predictive model, but what isn't a predictive model? A lot. Predictive models are not magic. They are not perfect, and they are absolutely not neutral or unbiased. When I say a predictive model isn't magic, it's really about what data went into it. For example, how representative and accurate was the outcome data you were able to collect? Did you have the budget to do a 10,000 person, you know, stratified on age, race, gender, geography, you know, kind of survey? Did you include texting as an option in your survey to get harder to reach populations? That kind of thing can cost some serious money. And that can be a blocker on getting really good representative outcome data. And so that's just a known limitation of models, is how good is your outcome data? Another question, how comprehensive and accurate is the input data? You know, I am really fortunate to work with a really great database that has tons of historical data, that has tons of commercial data, that's kept really up to date and accurate. But input data is not always perfect either. And so that, a model can't account for having insufficient inputs. And sometimes too, you find that your input data just, even if it's good and thorough, it's just not correlated with your outcome. And the model, the algorithm just can't find patterns. And that happens too sometimes. So a model is not magic. It has to have data that's there to make it work. Models are also not perfect. And I think this is a big one. Models work by quantifying our uncertainty. They don't make perfect yes or no predictions, right? So just because you're using a model to talk to people who you think are likely Democratic supporters, you're still going to talk to Republicans. And that doesn't mean the model is wrong. It just means it's a prediction. So let's take an example. This pretend probabilistic candidate support score. Note that this is probabilistic. If you talk to 100 people with scores of 80, you would expect fully 20 of them to actively oppose your candidate. So you're not gonna be talking to 100% supporters. Even with scores of 80 and higher, you're still going to be talking to people who aren't on the same page as you. And this is a perfectly calibrated model if that's your result. And not every model is perfectly calibrated. So models, they're not perfect. If you see a marriage score on a file and it says somebody is married and you talk to them and in fact they are unmarried, it does not mean the model is bad. It just means it's a model. It's predicting. It's not always going to get it right. So the last thing, and again, this is the most important part of this presentation. This is what I want everybody to walk away from this knowing. And this isn't just about predictive models in the democratic, progressive space. This isn't just about individual level predictive models. This is about every piece of data, statistics, model you will ever encounter. It is not neutral and it is not unbiased. Models are just a function of the data that goes into them. So if there is bias in your data, the bias is going to show up in your model. Models work by generating rules, and we've talked about this. What we haven't talked about is that those rules themselves are not necessarily particularly nuanced. Computers are stupid. We don't really, we call it artificial intelligence. I have a coworker who says it's a lot more artificial than it is intelligent. Human beings, we have brains that are capable of making, really interesting and nuanced connections really quickly. Computers can't do that. They make fairly rough rules using math. They can process large amounts of data. My brain can't process 240 million rows. But computers don't have that nuance that our brains have. And so their rules aren't always necessarily great. And so what can happen then is that any bias in data collection is reflected. And I have seen cases, I've seen, presentations at conferences where bias in the training data is not just reflected in the model. Due to the, rules generated by the model, the bias was in fact amplified. So what does this mean? Well, it means for me as a practitioner that I have to be very careful. Every time I build a model, I always do validations by different demographics. And then I always look at the score distributions by different demographics to see not only does this model work on different kinds of people, but is it giving different kinds of people, across the board higher or lower scores than other kinds of people? Because that will make its way into your universe, and that's how you end up only talking to a certain group of people. So it's my responsibility as a data scientist to always check for these things. And then, if I identify problems, I can't always solve the problems. There are algorithmic ways to address some of this, but a lot of it is data-based. And so it's my responsibility to communicate with, you, the practitioners, how you should use the model to account for the bias. But the model said so is never an excuse, because the model is just a thing that a stupid computer made. We are human beings and we know better. And so we have to be really careful. So I just told you a bunch of stuff about models that really makes them kind of sound like a bummer. So I will leave you with this. This is a semi-apocryphal quote from a statistician from the 60s. All models are wrong, but some are useful. And this is how I think about models. I don't expect them to be perfect. I don't expect them to be right all the time. I don't even always expect them to be unbiased, but I do expect them to do more good than harm, to do no harm, and to be useful. And so this is where I kind of want to leave you all, is thinking about models in this way. I love models. Hopefully you can tell that this is just my passion. And I'm really happy to answer any of your questions. Hopefully, I think some of you started putting them in the Q&A. So I'm gonna go take a look, but I will also give you some time, start doing your frantic typing. Let me know if anything's come up. All right. With these kinds of problems, particularly for individual level prediction, do you tend to use deep nets or shallow nets, or some simpler statistical methods common? My experience is more with time signal classification like speech recognition, where I've used nets for 40 years, but have been moving to the political domain recently. So this is a really good question. I tend to prefer simpler models because of the problems that I talked about in the final slides. I think it is really important that we, to the best of our knowledge, can understand what is happening in our models. This doesn't have to be regressions. We don't have to be able to look at coefficients, although that can be useful. And there are techniques like Lime where you can try to figure out like what is really going on, what's driving some of these predictions. But I'm a big fan of things like, you know, gradient boosted trees and good old regressions. I think will get you so much of the way a lot of the time. So I would say, like, if you're just getting into the political realm, go as simple as possible. Start with regressions, see how good you can get. Because we don't really have that kind of data that where, you know, deep nets tend to give you like a whole lot of performance boost. Let's see, somebody else asks, on the bias of models, do you expect scores to be less accurate in communities of color, specifically a democratic support score for the Hispanic community? So this is an empirically answerable question. We can do validations on folks on our file. We have a score that predicts somebody's race. And so actually, this is a really great thing just to point out. If you see a race on a file and it's national, it's a model, right? Like, we don't have everybody's race. It's not collected with every state's voter file. The Voting Rights Act used to give us race for some states, but now we don't get it. And we don't get it for every state in the country. So race is going to be a model in and of itself. Democratic support scores, you can validate them by race. You also, if you specifically are concerned about making sure that the model is accurate for that community, that's where you might want to collect outcome data specifically on Hispanic individuals, because that way you can be sure that your outcome data is representative of the group you're trying to predict. So I don't necessarily expect scores to be less accurate in communities of color. I would expect them to be less accurate if we didn't have representative input data. So hopefully that answers your question. We have another question. As a practitioner, is there a way to judge the usefulness of a model before you start using it? Lots of models predict support on specific issues, but it's not clear whether to use that or a general score, i.e. on progressivism. Ooh, I love this question. So this is something I almost put in the presentation, but cut it for time. So how do you know if you already have a model that does what you need it to do? And the answer is that validation chart with the stair-step bars. You can just do a survey. Start with a survey. Do you have data on whether or not somebody supports a specific issue? Take that survey data, line it up with the score that you already have. Is that prediction predicting that outcome? You can validate. You can validate models on different data. And so I would always say do a validation. If it looks good to you, and what good to you means is really up to you, it's up to your use case, then you might not need a new model. You might have a model that is already predicting what you need it to predict. Let's see, somebody else asks, if a model gives you something like a demographic, such as race, what is normally the confidence we should have that it is correct? So this is sort of gets into the question of different performance metrics on models. What I would say is the confidence, again, is that validation plot. You want to see people who have high scores on race having, you know, in real life, actually self-identifying as being of that race. So race is a bit of a tricky one because you can't do these validations yourself unless you have access to the probabilistic score. But you should always ask the data scientist who's building your model if it's a categorical score like race. You want to see the validations on the underlying score. They should show their work. So your confidence should be in whatever the release notes your data scientist provides to you. You want to see the numerical score. You don't want to see the category for that validation. This is what I would say. We are getting very close to time, but we do still have time if anybody has any more questions. I love your questions. I can feel the energy. I know that you are all remote, but I feel it, and I'm just so glad that we could spend this hour together. So please let me know if there's anything else that has come up. And just thank you for being here with me today. I hope that this has been helpful. I hope you've learned something. I hope that the folks in the room that are already practitioners and data scientists themselves don't think that I have vastly mischaracterized our field. And I hope the folks who don't have experience with data and models really felt like this was an approachable and interesting session. So yeah, I'll let you all just have a minute or so to ask any more questions. If you haven't filled out the sign-in sheet, Haley can send around the sign-in sheet again. Thank you. Somebody says thank you. So thank you back. Awesome. Well, I just hope that you have the best conference that you can possibly have, and I'm sure I will see you around virtually. Excellent. Well, thank you all so very much, and have a great rest of Netroots. So I'm just going to stay on the line for a few minutes before we close. So in case anybody has any more questions, I'm still here. But the rest of you all are free to go.